Thank you very much. That was fantastic. So I have the pleasure of introducing the next speaker, Wang. Dr. Wang comes from Virginia Commonwealth University, drove this morning here. He is, yes, Virginia, here we go. Fantastic. So Dr. Wang is an assistant professor and in the Department of Chemistry. He's a PhD. He doesn't treat patients with hypoparathyroidism, but he is doing something very special. He's interested in measuring minerals, among others calcium. And so he has dedicated a lot of work into trying to find a way to devise a self-measurement device for calcium. That's what we've been waiting for all year long, right? So there are many things I can say, but Dr. Wang talked to me one day about this, and I said, yes, there's a big need, right? And then he asked, well, what is needed, you know, what volume, what precision, etc., and how big, and blah, 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 and we talked. And then, you know, a year later at the meeting, he said, can we meet? And so we met. And he said, okay, you had these 5 different requirements. I did number 1, I did number 2, I did number 3, and I did number 4. What do we do now, right? So I'm very impressed by his work, which requires resources. So if anybody has an idea of having a fundraising for this enterprise, it would please talk to Dr. Wang. And I am happy that he came here today to talk about his development of a calcium measurement device. Dr. Wang.
So thank you very much for your invitation and the introduction, Dr. Manstedt. So my name is Wang, and yeah, I have a research group at Virginia Commonwealth University. I have a few research directions, including implantable sensors, bedside continuous blood sensors, and home use sensors. So I cannot use laser, okay. So the home use sensors, we focus on electrolytes, including calcium. So I had my PhD training in the area of ion sensors, where calcium is ion, so including calcium sensors, and then I did my postdoc in 2 research areas, ion sensors and glucose sensors. I was actually a GDRF advanced postdoctoral fellow working on glucose sensors and insulin infusion sets. So I do know glucose sensors and calcium sensors. So sometimes I got this question from patients. So why glucose meters are so well available on the market, and calcium meters, you can't find them. So what is the reason? Well, I try to share my personal understanding about the reason. Well, there's no standard answer, so I cannot guarantee what I said is definitely 100% accurate, but I do my best. So I want to show you the history of these 2 sensors to have a comparison. Well, glucose sensor is actually enzyme-based glucose sensor. It was invented in 1962 by a professor called Dr. Clark. So Dr. Clark invented an oxygen electrode first. So the electrode has a name of Clark electrode, actually, Clark oxygen electrode. And then he covered the oxygen electrode with glucose oxidase. Glucose can be oxidized by glucose oxidase in the presence of oxygen, and the oxygen will be consumed, and he uses his oxygen electrode to detect the loss of oxygen to indirectly indicate the concentration of glucose. Well, that is the first version of glucose enzyme electrode, 1962. And then after 13 years, 1975, the first commercial glucose electrode became available. It's from a company called YSI, that is Yellow Springs Instrument in Ohio. So after 6 more years, the first home use glucose sensor was launched by Bayer. So at that time, well, the analyzer, the glucose meter needs like more than 10 microliter blood. It has a brand name called glucometer. So it is actually a brand name, but because it's the first version, now we still call a lot of glucose meters glucometer, even though it's not actually glucometer brand. So while that is the first version, we know over time, home use glucose meters improved a lot. For example, it no longer requires like 10 microliter blood. It's a much smaller volume. And 1999, so the first continuous glucose monitor became available. So it is from a company, MiniMed. Later, this company was acquired by Medtronic. And 2006, the first artificial pancreas became available. So, well, this term means the closed loop system comprising a continuous glucose monitor and an insulin infusion set. So based on the reading of the glucose monitor, the dosage of insulin infusion is controlled to reach a desirable glucose level. So it's quite advanced level. Well, now if we look at calcium meter, it was invented in 1967 by Dr. James Rose at a company called Wang. So this company is actually in Cambridge, Massachusetts. So actually that is a professor, Dr. Eisman at Harvard Medical School, who was a consultant of this company. So that professor helped with the invention of calcium, the first calcium electrode. Well, 1985, in blood gas analyzers, so for the first time, calcium electrode was added into the blood gas analyzer. So if you go to a hospital, you have a blood draw, they can tell you the ionized calcium concentration by using this kind of calcium electrode. And then 1991, the blood gas analyzer became smaller. So Abbott had the first handheld blood gas analyzer, so including calcium detection function. That's 1991. I think many of you know the iStat product. What's next is blank. So after that, I'm not aware of a lot of progress in the area of calcium meters. So it's 30 years ago, 1991. So this is a huge disparity compared to glucose meter. Okay, so if we compare the status today, for glucose meter, for patient use, two versions, disposable or continuous. Disposable sensor for finger prick blood. The required volume is only 0.3 microliter, 0.5 microliter. So one small drop is 5-10 microliter. So you get any tiny drop of blood, that's enough. Very easy. The cost, well, $20, $50, $100 analyzer, and the strip is, well, very cheap. For continuous monitor, for glucose, nowadays, you know, the Abbott product, including the Dexcom product, they can last 14 days already with no calibration. How about calcium sensors? Well, nothing have been approved for patient use at home. Well, the only possibility is, well, it's not approved for patient use, but you don't have any other options, so you use iStat sometimes. But iStat needs 95 microliter blood. Think about the difference, 0.3 microliter, 95 microliter, that is a huge difference. So it's a lot of effort to collect 95 microliter blood from your fingertip. And the price is way higher. So again, the disparity is huge. Well, why? What's the reason? So I talk about the non-scientific reasons and the scientific reasons. Non-scientific reasons, easy to understand. So the market for diabetic patients, management of diabetes is much, much larger than the hypopara patients. So also for glucose monitoring, it needs very frequent monitoring. Calcium, at least not as frequent. Then you don't need so many strips, so many cartridges, and then the market is small. So I just show you one example. So there's a company, a startup company called BioLink. 2 years ago, it just raised 100 million to develop a new version of glucose sensor. We think it's already very good, but they try to make the needle even shorter, to have a micro needle array to make the sensor even less invasive, to further improve the life of diabetic patients. This is just one example. If you think about Dexcom, Abbott, Medtronic, how much money they put on glucose meters every year, it's a huge amount of money. How about calcium meters? It's about zero. If it's not zero, it's about zero. So I have an example. So glucose sensor is already at a very advanced level, but still they want to feed glucose sensor the best resources as much as possible. Calcium sensor is far behind, and nobody cares. So that is a very big problem, because sometimes we talk about like equity, inclusion. That is not equity, that's not inclusion. We ignore the calcium meters, we ignore the hypopara patients in terms of the technology, the diagnostic technology. So, well, that is the first reason. The second reason is research groups in universities, academia. So if you compare groups working on glucose sensors, hundreds of groups work or worked on glucose meters. Calcium meters, you can only find a few. There are many groups working on like a calcium bioimaging, but that's a different concept. That is not the meter for in vitro diagnostics. So it's another very big reason. And then scientific reasons. So actually, calcium meter is harder than glucose meter, very unfortunately. So why? Number one, so I showed two typical response curves of glucose sensor and the calcium sensor. So the left one is glucose sensor. The electric current, which is the signal, is proportional to the concentration of glucose. It's like if you have 3 millimolar glucose, you may have 300 nanoamp current. And if you have 20 millimolar glucose, you may have like 2,000 nanoamp current. So this linear relationship. And the glucose concentration ranges from 3 to 20 millimolar. I labeled this range using the pink area. If you look at the calcium sensor, the electric signal is proportional to logarithm of ionized calcium concentration. There is a logarithm there, which is very bad. Because of that, the calcium concentration range, also labeled as the pink area, is super narrow. Actually, most signal for the calcium sensor is wasted, has nothing to do with the clinical range. So if you look at here, it's wasted. But for glucose sensor, it's not wasted at all. So for glucose sensor, so the actual response is very large. For calcium sensor, for that clinically relevant range, is so tiny. That is very hard. That makes calcium detection harder. And number two, well, it's even harder to understand. Number two is glucose sensor has a baseline. What does baseline mean? If you have no glucose, so you have no current, it's zero. But calcium sensor has no baseline. If you have 0 calcium, I randomly put a 0 there, but that's a random number. So for electric potential, there's no concept of 0. 0 is always relative to a reference electrode. If you use a different reference electrode, this number can become 200, can become negative 200. So the reading for calcium is more random, and it's kind of flying in the air. It's much harder to control. So because of that, when you make 1,000 sensors or 1 million sensors, they vary a lot. They vary a lot. And then for the same calcium concentration, you will get many different results because the sensor is different. That's not what you want. So the sensor to sensor variation is very large for calcium sensor, but glucose sensor is better. And the worst one, the requirement for calcium measurement is even much higher than glucose measurement. Glucose measurement, if you have 20% error, not a problem. And some initial products have 30% error. It's like 20% error means if your actual glucose concentration is 5 millimolar, the result from the sensor may be 6 millimolar, maybe 4 millimolar. So this kind of error. It's not so bad. But calcium, so typically we want to have an accuracy of like 0.1 milligram per deciliter. It's much smaller than 5%. The sensor itself is so hard and the requirement is much higher. That's the problem. So it's not very easy. So sometimes we think, well, glucose sensor is so well established, its success should somehow help with the development of calcium sensor. But unfortunately, they are not similar at all. So they are completely different. The design, the signal, the recognition mechanism, everything completely different. So glucose sensor does not help with calcium sensor at all. That's very unfortunate. So, okay, our group works on two directions. So we try to solve the problem of sensor-to-sensor variation and the too small response because the range is too narrow. So we try to work on these two things. Well, I want to clarify one thing, that is I'm a chemist and I'm working on something quite fundamental. So I do not have a beautiful product to show you. But I think I'm laying the foundation. That is more important. Actually, it's very easy to show you a product, but it may not be accurate. It looks very beautiful, you are very excited, but the inside, yeah, could be very problematic. So I won't go into details, but the first thing we did is we developed unselective electrodes with the baseline. I mentioned unselective electrodes, well, which is the calcium meter. The technology is called unselective electrodes, have no baseline, but we somehow are able to create a baseline. Because of that, we dramatically reduced the sensor-to-sensor variation. So if it's a regular sensor, they easily have like 50, 60 millivolt variation. It means an error of about 1,000%. That's huge. So that's not better than guessing. But with our new design with the baseline, so the error becomes 1 point something millivolt, which is an error of a few percent, so which is much, much better. So we call this self-calibrated unselective electrodes. Well, but we actually focused on potassium in our first publication. The reason is very simple. Potassium detection is slightly easier than calcium detection. So we focused on potassium and we tested multiple blood samples. We proved our method has a lot of promise compared to other methods. We have much better accuracy. So I want to summarize the status of this technology. I don't want to go into technical details because this is not a chemistry conference. Well, so we filed international patent for the technology, and we also published the first paper using potassium as example. So very fortunately, now we have a fund for this direction. We have an NIH grant, and we also have a grant from Virginia Commercialization Fund. So now we are able to include calcium because that is in the specific aims. So in the beginning, we don't have money. Well, we can choose the easy one, potassium easy, we do potassium. But now we have to include ionized calcium. So, well, but this is a very big change compared to traditional sensors. And there are a lot of fundamental things to understand, and it will take a while. It will take a few years, at least. It won't be available like in 1 or 2 years. And another thing about this method is potentially it could become a continuous calcium monitor because this is electrochemistry. We can make a small electrode and implant it under the skin, just like the continuous glucose monitor. So it has this potential. So this method one. So the second technology is inkjet printed paper-based sensor. The reason for doing this is we want to reduce the sensor-to-sensor variation to fabricate identical sensors. And we know inkjet printing can print things very consistently, precisely. So we actually pioneered the inkjet printed on sensors. So we have the dye on paper, and then if we have different concentrations of calcium there, it's different color. Well, we published a lot of papers, and it's very good. And then we try to detect the blood. Here's the thing. You can't add a drop of blood onto this sensor, because otherwise you will only see one color, that is red, all the time. So you have to have a plasma separation membrane. So you have the sensor and then plasma separation membrane, and then you add blood. Only plasma diffuses across the separation membrane to reach the sensor to change the color, but the red blood cells are trapped. That's the only possible design. We worked very hard on that. What we found is the plasma diffusion is not so uniform. We tried many different stacking methods. We tried vertical flow. We tried lateral flow. It's always not uniform enough. If it's not uniform enough, the error is large. The sensor is identical, but the entire device is not identical enough. And then it's not good enough. Well, but Dr. Manstead mentioned the urine detection. Then, if we think about this technology, it may be very easy to do urine detection, because urine at most is yellowish, so we can correct that color, but it's not like dark red. And this is very cheap, very easy to fabricate. We can print some kind of dipstick for you, the strip, and you can dip it into the collected urine. So, and then you have a smartphone to take a photo, and we have an app to tell you the calcium concentration. That is certainly possible, but we didn't pursue that because we have been focusing on calcium in blood. Well, this one didn't work, but we can't simply give up. So we think, how can we avoid using plasma separation membrane, which is the problem? We found this new design, that is, we have a segment of liquid sensor. Liquid sensor is like, think about some kind of oil, for example, soybean oil. I add some sensing dyes into the soybean oil. And then I have this kind of design. The oil is in a capillary tube or a pipette tip, and then we aspirate a small drop of blood into the tube, and then we do mixing. At the end, we check the color of the oil using a smartphone. Then you don't care about the color of the sample. It's red, it's transparent, it's whatever, because you only pay attention to the color of the oil. The oil is next to, is adjacent to the sample. They do not overlap. They do not cover each other. So by doing this, we can detect the whole blood without any separation of blood. So that is a big deal. And also, we found we have very good reproducibility, meaning sensor to sensor variation is very small, because liquid sensor is very easy to prepare. Well, the detector is also a smartphone. So it looks pretty complicated, but for a patient, what you need to do is you insert a disposable capillary tube with the sensor preloaded into a stepper motor, and then you add a drop of blood at the end of the tube, and that's all you need to do. The rest is done by the machine. So it's very similar to the glucose meter as well. You insert something and add a drop of blood. Even though the device will be larger than the glucose meter, it may be this size, but I don't think that is a huge problem. So as long as it is convenient for patients. So actually we had a, I call it breakthrough for the colorimetric response, because I showed you the response is always wasted a lot because the detection range is too wide. So that is also true for colorimetric sensors, not only for the electrodes, both. And this is what I showed. So the response range is so wide and the actual range is so narrow. We are able to detect, we are able to develop new chemistry that shows an extremely steep response. We call this gate-like response. So only for the clinically relevant range. So we do not waste any signal. Our color changes from blue to yellow. It only happens for the clinically relevant range. So this is a very big deal in my opinion. So for example, here we have 1 millimolar calcium to 2 millimolar calcium. The color changes from blue to yellow. It's a very big color change. You can tell it easily from your eye. So, and we tested whole blood. So you can tell here, we have triplicate for each blood sample. And I have 5 blood samples with an increasing concentration of calcium. You can clearly tell first, the reproducibility is very good. For each triplicate, there's no difference in the color change. So it's the same color change. And also, the result for whole blood matches the result in standard solutions very well. So we tested 51 blood samples, and the overall error is very good. So for most samples, the error is below 5%. That is very encouraging for a brand new concept and a brand new chemistry. So, so for this one, well, first, I work on this direction because of the fund from Orphan Disease Center 2-3 years ago. Otherwise, I don't know this need, and I won't work on this at all. So, and then I want to thank Calcilytics. So they provided fund so I can develop the extremely steep colorimetric sensor for calcium. Otherwise, it won't happen. And we published the paper, and we also filed the international patent. And currently, we are trying to get new fund so we can integrate the hematocrit, and we can do some more blood samples. Actually, we got our IRB protocol approved in August at VCU, so to test samples from real hypopara patients, so we can have a much wider range of calcium concentration. So that is ready. And we are also working on many other aspects like engineering, like commercialization, and hope to push this direction to a reality, because I think this will take much shorter time than the electrochemical method. And my goal and my dream is to commercialize this in a few years if we have enough resources. Okay, so I want to end my presentation with something more positive. So calcium detection is not alone. The challenge is not alone. Actually, there are a few companies which are developing at-home monitors for other blood electrolytes like sodium and potassium. They typically share the same platform. Yes, definitely they need some adjustment optimization, but if somebody can develop a potassium sensor, sodium sensor, it may be used for calcium as well. So that is some more hope. Okay, so my postdoc and my students did the work, and we want to thank the funding agencies again. That's all I have. I'm happy to answer any questions.
Thank you very much. Thank you so much. Do we have any questions in the room before we go online? Okay, Michelle.
I want to say thank you. And when you get to the commercialization process, the Department of Pathology and Laboratory Medicine at Indiana University would be happy to be a host site. I've got a large industry-sponsored trials group. I employ med techs, and we will give you the friends and family discount. So keep me in mind, okay?
I appreciate that.
Hoosiers will help you.
All right, anybody else? Questions? All right. Well, thank you so much, Dr. Oh, we got one? Oh, here we go. Sorry.
Three or four people just popped up online also to say thank you very much, and thank you for taking notice of our population and for continuing your work even though there's such a small portion of us. We really, really appreciate you putting in this effort and explaining to us why it is not so easy to make a calcium monitor, because I know a lot of people think that you can just take the glucose monitor and modify it, and you've done a very great job today of explaining why that is not possible. Thank you.
I'm dedicated to this. I will try my best to make this work.
I had a question whether your device is intended to be an at-home or whether it's intended to be portable.
Both, so portable,
Okay,
so that
it
it
can
be used at
handle
home.
being stuck in a pocket and walked around with.
Well, it's not that level of portable. I
yet.
cannot guarantee, but it can be. You can move it.
Okay.
Yeah, you can carry it, but not in the pocket probably.
Okay, that's fair.
Okay,
Just
there-
curious.
There are some questions popping up online now. Did you do any iStat comparisons?
Well, we are testing total calcium. We do not use iStat, but we did have a commercial total calcium test kit as the reference method.
Okay, and there's a couple people wanting to know, is there a way they can watch your progress? Do you have a website or anything that they can look at?
I have a website, but I unfortunately do not have details on this specific direction, so I will add it.
Thank you.
All right. Well, thank you again, Dr. Wang, for your time this morning. And for everybody, we are having lunch again in the lobby out there, and we'll be back in the room at 12:50. So enjoy, and thank you so much again, Dr. Wang.